Just one thing to mention also is that now I use synthetic data, right? But what if you have real data? So what you can do then is go to Files here. And here you can do, you can upload, create a directory, and you can upload a file, for example, a CSV file or an NumPy file or whatever you want to load in your data. And then from here, if you just do here, you will see that you can access that data from your home directory. Okay, so that I think is all that I will show you. How long did I go for? Pretty long.
It's we have, I think, about 50 minutes left. So
yeah, that's good.
I thought that was great. Thanks so much, Fredrik.
Yeah, thank you, Fredrik. So are there any questions for Fredrik?
Oh yeah, sorry. Any questions?
Just unmute yourself and ask or write in the chat in that case.
I just had one question. You were saying that like you could tell how long something was running. Where did you look to see if you said something running or not?
How long it runs?
How did you see where it was running?
Do you want to share your screen and show the little icon, the running icon in the notebook versus the not running icon?
I'm not following what you mean.
So Jamie, I think what we're looking for is like, and I'll show this maybe just in a second, but those notebooks, there's a little number just to the left of it, and it says in and then bracket, and then if there's a star there, it's currently running or scheduled to run, and if there's a number there, it's completed running.
Yes.
Okay, I see.
Exactly.
Thank you.
And actually, what I hope we have in the future is that I showed you this dashboard, dashboard, that you could, when you had the where I defined the Dask client, and if on that link actually you can see all the tasks that are being computed as a progress bar, which is very neat. So we hope to have that in the future as well. So you can follow actually progress of simulations in real time and see when it finished up to 100%. That would be much even more clearer as when it has completed, right?
Good. So Jamie, I was curious, are you doing this type of modeling in your work, or?
So right now I'm working on like enzyme reactions on lipid surfaces motivated by coagulation. So I'm interested to see how I could maybe load my model in here and try to play around with it without having to like recode everything every time.
Yeah, cool.
Sounds cool. Sounds cool. All right. Other questions for Fredrik? If not, we should move on with Brian, who wants to show some more what we call advanced features.
Yes, indeed. So I'm going to share my screen and go on to StochSS Live again. Let's see, share. And then just to confirm, everyone can see my screen here.
Brian, you might want to turn up your volume a little bit.
Am I quiet? How about this? I'll just speak
That's
up.
good.
I don't know if I have volume input device. Actually, I do. Yeah, just let me know. Is this okay? Testing.
Yeah.
1, 2.
But what's the sort of the sound in the background?
Oh, I think that's just my computer fan.
Oh.
At least my computation finished before this happened. Fredrik noted it was very loud when we got started. Hopefully it's much quieter now. Yeah, I'll go ahead and get started here. So yeah, we're sort of picking up where we left off yesterday. And I just wanted to mention one thing before we got started, that this StochSS registration. Now, this isn't required to log in. However, we're supported by grant funding, and the more users we have registered for our software, the better chance we have to continue to support the development of these techniques, these tools, and to host StochSS Live. So Please register. It doesn't take, we won't share information with anyone besides funding agencies, and then only in aggregate. Without registering here, I'm going to click login, sign in with my Google account. I'll choose my professional Google account. Oh. That's always good. I think this might possibly be because I was logged in before. Oop. This is the fun of live demos. Let me just see. Here we go. Okay, so this was simply a feature of me having logged in just prior to this and logging out, and my Docker container not actually shutting down. So all I did was go into the server, shut it down, come back. For anyone else, this should just happen automatically. Let me get back on track here. So this setup, I'm going to go back to browsing my projects. Got all my projects here, the mini tutorial live. I'll just continue on with this particular project. And the first thing I want to show is that, Jamie, I think you mentioned importing other models. So reproducibility and distributing your models is a very important piece of simulation and modeling in general. So SBML is sort of the standard within the systems biology community for specifying models, and the biomodels database is a large repository of SBML models. So we can go to this Nielsen 1998 paper, and this one is, let's see, what is this? Sustained oscillations in glycolysis. So I can just go here to files. See here we have this XML file, so I'm going to go ahead and just download this file here. And then this file, I can come back over here, say add model, and right. Believe yeah, so we should be able to add model. You can do this normally, but here I can say upload SBML model. So now I'm going to choose, I'm going to go to my desktop, and here's that file I just downloaded. Double click on this, upload, and this automatically converted it to an SBML model, and now it just automatically shows up in my list. If I didn't like that name, I could have entered that name on the upload panel. But now I can click on here, and you can see that I have a fairly complex model. So we have quite a few different variables or species. set in here with their initial conditions. We can look at the parameters. So this is by default a concentration model. SBML models are always by default concentration. We have a large number of parameters, all specified, and all these reactions. So these have been automatically imported, and we've done some validation to ensure that that's actually working correctly. So I can just go, click Simulate, Preview, and here is my SBML model of glycolysis, and this should sort of provide an example of what we can do with these. So, in just seconds, really, I was able to download, upload, and run this model. And then, further, let's open this up in a parameter sweep. Detail here, and then we can say one parameter. So let's go with two parameters. Let's do, K1 GLC, K1 ATP. Run this, choosing for me. Start workflow. Okay, what variable of interest we're gonna look at? We're gonna look at P. This should take just a second here to run. Maybe slightly more than a second here. Oof, this is taking quite some time. I'm surprised by this. So I guess I'm going to skip back to the project here. This should finish in the background, but just to show how powerful this is, I'm going to open this up in one of the notebooks and show how easy it was to go from SBML to importing this entire model with all of its large number of reactions, species, and variables right into GlossPy 2. And we can just do cell, run all. And this is what I wanted to mention. So we have 1, 2, 3, and then you can see up here on the right, this kernel is dark. That means that this cell is currently running, just not surprising, model.run, definitely takes the longest amount of time. So these numbers are output sequentially within the Jupyter Notebook. And of course, I did this for 100 trajectories. That was that was sort of a mistake. So let's stop it. Change this back to 1 trajectory. And then, ooh, dead kernel. No problem. Restart, run all. Perfect. Okay. Yeah. So that took a much shorter amount of time, and you can see that this plot is pretty much exactly that plot. But I can download as a PNG or edit the axes. There's quite a few properties that you can do of this plotly here. So if I hit B down, question mark, shift return, this will give me a lot of the documentation on exactly what you can do. And you can see you can use this to edit layout, title, axes values, all these things you're going to need to do to create a production publication ready figure. Okay, fantastic. Going back here, so that was using SBML import. So then the next thing I wanted to show you is something else, some other very useful things we can do with GLUSPy2. So I'm going to copy the address here. So I'm going to go to the GitHub page for GLUSPy2, and this notebook is in the general thing, but here is our GitHub page. We've got lots of information, how to install, etc. like that. What's really useful actually is we have our examples folder here, and then inside of the data visualization folder, we have a couple of different examples of how to do that. So I'm going to go to this live output. It's really great that this is sort of rendered for us by GitHub, but I'll go ahead and do to download this. You have to click raw, and then I'm going to save this to my desktop, live output. Now I'll warn you, if you're using a Mac, I've found that it always adds a .txt to the end of that. So you have to remove that .txt for this to work. So now I'm going to go here, browse my files, and then I will be able to upload file, choose file, here's my desktop again, live output, open, file name, I guess I'll show you. So this is mini tutorial live output.ipynb. And then mini tutorial live output ipynb. I'll double click that. Close this now. And here we are with the live output. So shift return to execute the first cell. That executes, now there's 1 next to it. So the example model that we're going to use for this live output now is going to be the Velar Oscillator. So this is an oscillating chemical system, sort of a standard model within the literature. So shift return to that, create the model object, shift return to that, run with live output. So now we're going to set this example as live output. So instead of just running, we're going to have it run and live output text. So we're going to run it up to 200. You can see here, it's just spitting out each of those times. So this is actually the simulation time, and the wall clock time, the real time, is about every second, although that's a configurable thing. So now I'm going to go ahead and stop this. So it ran for 16 seconds. And then I can just hit plot, and this will give me the plot out to, let's see, it was 125 was the last thing. So if you look here, yeah, it's right about 130 or so. So after the last reporting, we got a little bit further, but you can see that we're getting this nice classic Velar Oscillator oscillations here, the peaks and the valleys. Now what I'm going to do is resume the simulation. So I started it, I stopped the simulation after just a few seconds to see what it was looking like. Very useful if your simulation is going to take a very long time. So now I can resume it. So I'm going to say same solver, output text, live output options every 2 seconds now. And then this resume equals results1. So when I ran the first time, I said results1 equals model.run. So this produced a results object. This is going to produce a results2 object that picks up where results1 stopped and continues on. So I'll run this. This is going to continue on. Let's see, it's going to go all the way to t equals 300 because that's what I specified here. Note that this is different than t equals 200 or even what I specified in here. So we can you can sort of override this, and this should go to 300. Yep, perfect. You can plot these. And then got those same oscillations going out a little bit further. So let's finish the simulation. Using the NumPy solver. I think that's a slate mistake here. Great. Okay, so here's the different output. Now we're going to finish the simulation. So we're going to resume from results2 to create results3. We're using the NumPy SSA solver, but this time we're going to do progress, which is just a percentage. and output every 0.2 seconds. So this will get us to the end here pretty quickly. Now, what I will say is all of these actually slow down the simulation a little bit. Outputting can be very expensive. So if you're just looking for performance, this isn't the way to do it. However, it's very difficult to a priori decide how long a simulation is supposed to take. So we can do results 4. This is going to be progress again, and I'm going to go up to t equals 600. Let me see this. And then just to point out, everything I've done so far has been with the SSA solver. So we're using discrete stochastic simulation here. But the resume feature doesn't require that. So I can add, let's say, results 5 equals model.run. And this time, I'm going to change it from the SSA solver to run with the ODE solver. So I'm going to change it to run it with solver equals ODE solver. This is going to make it continuous deterministic. Let's see, I'll do progress. I'll do the rest of these the same, but I want t equal out to be a little bit further. So we'll go out to 700. Oh, I'm sorry. I actually want that to go out to 1,000. Oops. And then results 5.plotly. So you can see we have quite a few different items out here, but if you look at the first number of the earliest, it's all integers. And out here should be possibly floating point values. Doesn't look like it. Perhaps it's being floored. Nope, I'm sorry. Of that pair of numbers, it's xy. So y is the value of, in this case, the species r. So you see that's 1284. Out here, you can see now it's floating point values, 925.674. So we've taken a results object and incorporated both discrete stochastic and ODE simulations together in the same object, and we can just plot those. So those work together. So yeah, this is sort of just another feature we have of let's see what's the time. Okay, feature we have of the of GLESS 2. So